Hello, welcome back to Chemistry 2341. We're going to do homework for Chapter 3. All right, so let's get going with this here. So the first one is 3.7 from inside the chapter. Using the pKa values of the analogous compounds from Table 3, predict which is going to be the stronger base in each pair. So let's look at the first one here. Okay, so those are both bases, but pKa's, we have to look at it from an acid point of view. So what would the conjugate acid of each of these things be? So the first one would be this OH, which turns it into phenol. So we have to look at the pKa for phenol. And then this would be just a isopropanol. So we would have to do it for an alcohol. So if we look at the table right here, and we find phenol on the table, we see that phenol is right here on the table, and it has a pKa of 9.9. And we see that alcohols, right here, this is ethanol, has a pKa of 16. Okay, so that means that this has, let's say, call it this 10, the pKa of 10, pKa of 10. Try to erase that. There we go. Aha. pKa of 10, and this one had a pK of 16. Okay, so which of these is the stronger acid? Okay, so phenol is going to be the stronger acid because it has the lower pKa. Okay, but remember, base strength is the opposite. So if phenol is the stronger acid, that means the conjugate base of this compound is going to be the stronger base. Okay, so this one is going to be the stronger base. All right, let's use that same argument for the next one and look at that. Oh, it is the T-butoxide versus the acetylene ion. So that means we need to find the pKa of this versus the pKa of this. So if we go to our table real quick, we'll see that the T-butoxide right here is on the table even, is 18, and acetylene right here is 25. So let's use those values back here. So this is 18 and this is 25. Okay, so which of these is the stronger acid? Well, this one has the lower number, so it's the stronger acid. If this is the stronger acid, that makes this the stronger base. Okay, do we see how that argument works? Let's do that same thing for these last two. And we're going to see that the pKa of, let's see, we have to turn each of these into an acid. So to do that, we have to do a nitrogen, and it has to have a proton on it. So it's going to be this structure here. So we have to look for an acid on our acid table that has that nitrogen with 4 bonds to it. And we have to look for something with a proton on here. So these would be their acids. Those are the acids we need to look for on the table. All we've done is added a proton to both of them. Let's go look at our table right here. Let's see, do we have anything that looks like, ooh, this is an ether with an OH on it right here. And it has a pKa of -3.8. And let's find a nitrogen with, oh, here we go. Let's see, a nitrogen with, okay, an alkyl group on. So this looks like the closest one we have right here. It has a pKa of 9.2. -3.8 and 9.2. So we have 9.2 and -3.8. Okay, so which is the stronger acid? This is the stronger acid. So that would make the conjugate base of this one the stronger base. Okay, so we'll do that last one again. So we have acetic acid right here, or a carboxylic acid. And then this is a carbonate if we put those protons back on. So we're going to draw those protons back on, OH. So we're looking for that structure, and we're looking for OH, OH. So let's find out what the pKa's of those are. And if we look at those on this table here, we're going to find that, let's see, the carboxylic acid, we know it's going to be around 5 somewhere. So here's the carboxylic acid. and it's 4.75. And look, right below it, that's the carbonic acid. That's the other one, and that's 6.35. So let's go back to here. So we have 4.7 and 6.35. So which one is the stronger acid? Acetic acid. So that means that the ion of the carbonate is going to be the stronger base. Okay. Now, let's move on to the next question. Okay. What is the conjugate base of each of the following acids? Okay, so whenever we think about conjugate bases, we're talking about Bronsted-Lowry, which means we have to remove a proton. Okay, so let's start with the first one, ammonia. So if we had NH3 and we removed a proton, we would go to NH2 with a negative charge. Okay, so this would be the conjugate base of that. If we have H2O, we remove a proton, that'll be HO minus. If we have hydrogen bonded to hydrogen and we remove a proton, remember we're removing a proton each of these times, that's going to turn it into H minus. Okay, and that's one of those interesting bases we have. And then this is a triple bond here. So if we have C triple bond C with an H and an H, we removed one of those, we get to C triple bond C with a negative charge on it, and hydrogen over here. All right, so let's see. So this is the most acidic hydrogen on here. So we're going to go from CH3OH to CH3O minus. So that's going to be its conjugate base. Oh, and so we have H plus, and we're going to remove one of these protons so that we're going to get back to HO. So that means water is the conjugate base of the hydronium ion. Okay, do you see how we did that? All we did was remove one proton and then leaving the electrons on the conjugate base. So leave the electrons on the conjugate base. All right, moving on to 21. What is the conjugate base? List the bases that you gave in problem 20 in decreasing order of basicity. Okay, so we have to use that table again. So let's look up the pKa's for these on that table. And if we look up the pKa for ammonia on that table, we'll see it's 38. And the pK of water is 15.7. Let's just round that up to 16. We should be able to tell the difference. 16. Hydrogen, if we look on that table, it's way up there, but it's 35. This alkene, I think it's an alkyne. Alkyne would be 25. And then the alcohol would be 16, and the hydronium ion is minus 1.8, 1.7. Okay, so that being said, let's put them in order of acidity first. 1.7 minus 1.7. So we want to say list the bases in order of decreasing basicity. Okay, so if this is the most acidic, and then the next most acidic is going to be water because it's 15.7. And then we're going to have methanol. And then we have acetylene. Then we have hydrogen, and then we have ammonia. Okay, these are increasing acidity because we put them in order of their pKa's. That means that we've now also done our order of increasing basicity. That is incorrect. Our acidity is increasing in this direction, right? Because this is our most acidic compound, which means our basicity is increasing in that direction. which means this one is going to give our strongest conjugate base. This is going to give our weakest conjugate base. The weaker the acid, the stronger the base. Okay, so see how we can use the pKa's to order things from acidic to least, most acidic to least acidic, and then know where it would fit on the basicity scale. All right, moving on to the next one here. What is the conjugate acid of each of the following? So in the case of conjugate acid, we're going to add a proton to these things. So in the case of H2SO4, we're going to add a proton, which turns it into H2SO4. Since HSO4 it has a negative charge, we added a proton to it, it gets back to neutral. Okay. So in the case of this, we're adding a proton to it. So we're going to end up with an OH. But we've used up one of the lone pairs to create that new bond, which means we're going to have a positive charge. Okay, so in the case here, we have a neutral. We have nitrogen with hydrogen, and CH3. It has its lone pair. We're going to take that lone pair, bond it to a hydrogen, and we get a positive charge on nitrogen. All right, in this case here, we have H2 minus. These electrons are going to form the bond with hydrogen, making our final structure NH3. So all we're doing is adding a proton to a lone pair or the negative charge. Okay, so in this case here, we have it looks like we have a negative charge on that carbon there. So we have a negative charge on carbon here. And it means when we add a hydrogen to it, it's just going to turn it into ethane. Okay, and our last one here is CO2 minus with a methyl group on it. So that means it's a carboxylic acid salt. And if we add a proton to it, it'll turn it into the carboxylic acid. So these are the conjugate acids to each of these bases. You add a proton. Okay, and list the acids in the problem in decreasing acidity. So let's look at the pKa's again for this. The pKa for sulfuric acid is really strong, -9. Carboxylic acid is 4.75. So we have -9. We have hydronium ion, which is up here at -1.7. -1.7. We have the protonated nitrogen compound, which is right here at 9.6. I'm sorry, 10.6. 10.6. We have ammonia, which is way up here at 38. We have the ethane under here, the ethane here at 50. So this would be 50. This would be 38. And our last one here is at 4.7 right here. So let's list those in acidic order. So obviously the sulfuric acid would be first because it has the lowest number, followed by the hydronium ion, followed by, let's see, we have the acetic acid here would be next. Then our protonated nitrogen here, then our ammonia, and our last one would be the ethane. Okay, so that's pretty straightforward. Okay. All right, so rank the following in order of increasing acidity. Remember, there's 4 things we have to worry about acidity. 1 is the element, 2 is the hybridization, 3 is resonance, and 4 is inductive effects. Okay, so we're all dealing with oxygen here, so we don't have to worry about the element. So the hydrogens are on all the oxygens. Again, they're on oxygen, so we're not changing our hybridization. So all we're caring about is the resonance and or inductive effects. Okay, so this has a double bond near it, so we can spread negative charge. So it has a resonance structure possible when we make our negative charge. This one also has it, and the carboxylic acids both have resonance, making them more acidic. Okay, So that means that this one right here does not have resonance. There's no double bond for it to spread that negative charge out. So that's going to be the one without resonance, okay? So this one, because it doesn't have resonance, this is going to be our least acidic compound, just from that. And what we know is if we have this compound and this compound, we know that carboxylic acids tend to be more acidic than phenols, because the things we need to remember are phenols, alcohols, and carboxylic acids at 5, 10, and 15 respectively. So this is going to be somewhere around 15, and these are going to be somewhere around 5, and both of these are going to be somewhere around 10. Okay, so that means that this group here and this group here are our next set. Okay, so that's our least acidic one. So let's talk about these two here. So we've already done our resonance in that. So now we have to go to inductive effects. So in the inductive effect, we have a group right here that has lone pairs. So it can donate electrons to the, I'm sorry, that's the wrong arrow. It can donate electrons to the ring. So it can make this, it can add electrons to the ring. Come on. It can add electrons to the ring. Ooh, but this one right here, this nitro group, that takes electrons away from the ring. Ooh, not that one. This one has a CF3 group. It can take electrons away from that ring through the inductive effect. Which one's going to help acidity? Okay, we want that negative charge to be more stable to make it more acidic. So in the case right here where we're removing electron density away from where the charge is going to be, we're going to increase its acidity. So this one's going to be more acidic than this one. Okay, so this is going to be, this is 5, this is 4, this is 3 so far. Okay, do we see that the stabilization of that negative charge happens in 4 of them because of resonance, making them more acidic than the last one? And then just comparing between the two that are the same structure, it's the inductive effect that changes it. Okay. So now let's do that same thing here on these last two. We already have the fact that they are the most acidic because of that carboxylic acid. Now let's look for inductive effects. Here we only have a hydrogen, and here we have the CF3 pulling electron density out. So just like with the halogen close to those carboxylic acids, having that electron group makes it more acidic. So that's going to change this to 2, and that's going to make this one the most acidic of our set. Okay, so whenever you look for acidity, look for element, look for hybridization on carbons, if it's a hydrogen on carbon. Resonance, can it do more than one stabilizing structure? And then inductive effects. And if you go through all 4 of those, you should be able to identify and rack and stack the acidity without a table. Without consulting the tables, select the stronger acid. Let's use that same thing, okay? So luckily we only have pairs. So we have something that does not have polar bonds on it and something that has a strong electron withdrawing effect. So what's that going to do? That's going to make the negative charge formed here even more stable. Therefore, this is going to be the stronger acid because of the inductive effect. Oops. The inductive effect. So let's look at this again. We have the CH3 and the NO2. The NO2 is a strong withdrawing group. Therefore, that one's going to be giving us the stronger acid. Ooh, we have 2 NO groups. Okay, now this is a little harder. Okay, so now we have to look at the resonance here, because if we have phenol, OH, and we put a negative charge on it right here, put the negative charge on it here, and we want to share that around the ring, what's going to happen? We're going to have this electron come in here, giving us a negative charge here. And then, because these electrons have to come up here, then through resonance, we can move that negative charge from here that negative charge to here, and that negative charge back to here. So let's look at all four of those resonance structures real quick, just to see that we see where they are. We're going to start with the first one and our O minus with double bonds all the way around the ring. We're going to do our second resonance structure where we have O with a negative charge here, and our other two double bonds haven't moved. Oops. Change these up. Okay, double bond here, double bond there, double bond there. These electrons will pop up to here, giving us a negative charge here on this other isomer. And then that's in resonance with moving these electrons down and these electrons up to give us negative charge here and the double bond there. And then, of course, it'll go up the other side to give us the other one. So what this is giving us is the idea that of our resonance structures, I'll draw it over here, we have the ability of moving that charge around the ring by that conjugation. Now, let's look at where those negative charges ended up. Those negative charges ended up on this carbon, and on, change colors here. Our negative charges ended up on this carbon, and this carbon, okay, in our resonance structures. Okay, so what we're going to see is that this positive electron withdrawing group is on the same carbon where we're going to see a negative charge. So that means this is going to have a higher impact on the acidity than having it not be on that group. So the inductive part, they're both the same. But by resonance, this one's closer to that withdrawing group, and therefore it's going to be the more acidic. So we used, in this case, just the inductive effect. We used, in this case, just the inductive effect. But in the third case, the inductive effect was the same for both. We had to use resonance. All right, so let's go to number 26. Designate the Lewis acid and Lewis base for each of the following reactions. Now, the first thing we should look for is the electrons. So if we draw all four, if we draw the electrons, the three lone pairs on this chlorine right here, and we know that the aluminum doesn't have three electrons on there, that makes the chlorine our Lewis base. So these electrons are going to reach out here and attach to that aluminum. How do we know that happened? Well, in our product here, we see a bond between the aluminum and the chlorine. That means that lone pair from the aluminum, or the lone pair from the chlorine, is making that new sigma bond with the aluminum. Therefore, this is the base, the Lewis base, and this is the Lewis acid. Okay, so let's look at the second one here. Again, what we're going to do is we're going to draw our lone pairs on here and look at our product. Look, right here, we have a bond between the oxygen and the bromine, the boron. And so what's happening is our lone pair is reaching out and making a new bond with the boron. That makes this the Lewis acid, a Lewis base, and makes this the Lewis acid. So if you're not sure, see where the bond was, and you can note which electrons were used to make that bond. So let's look at this one. That one's going to be interesting. So we have a new carbon-oxygen bond. So if we put lone pairs on this oxygen, these lone pairs are the ones that are going to come here and make that new bond with oxygen, the new bond with carbon, and therefore this is the Lewis acid because it's accepting those electrons. This is the Lewis base because it's donating the electrons to make that new sigma bond. All right. So let's go on to number 30. What reaction will take place if ethyl alcohol is added to a solution of, and that looks like acetylene to me, the acetylide ion in liquid ammonia? Okay, so let's see. We have OH plus H, triple bond there, negative sodium plus. What's going to happen? Well, okay, what could happen is that we could transfer a proton from here to here, because it's an acid-base reaction, and that would give us a salt of the alcohol and. So all we've done is transferred this proton here, but wait, hold it. We don't draw our things like that. We draw it from where the electrons are flowing, right? So what we're doing is the electrons from this are coming over and taking that hydrogen. The electrons that were in the bond with the hydrogen are going to be on the oxygen. So that gives us our, this is our Bronsted acid. This is our Bronsted base. And that makes this our conjugate base and our conjugate acid. Okay, so that means that we have the reaction is going to go in there. Now, which way did the reaction, which way did the equilibrium lie? We have to compare the acid strength on this side to the acid strength on this side. And since we know the pKa of alcohol is 16 and the pKa of this is 25, let's see, what does that mean? That means the carboxylic, so it always goes from the strongest acid to the weakest acid, right? So this is the stronger acid, this is the weaker acid, which means the equilibrium is going to go in this direction. Okay, let's see. The next question is 31. The Ka of formic acid is 1.77 to the minus 4. What is the pKa? Well, the simplest way to do it is just say, oh, we can, the log 10 is going to be pretty close to minus 4 because of, you take the exponent down. If you actually did the calculation on your calculator, it's going to be minus 3.77. Okay. So that means if we have a Ka that's 13, we have a pKa that's 13, what would the Ka be? It would be something on the order of 10 to the minus 13. But it's just because it's the law, you're going to take it to that power. Okay, so 32. Oh, we're not doing 30. Okay, so these are 38, A, B, and C. We're going to start with this. Supply the curved arrows necessary for the following reaction. Okay, we definitely want to see where everything's going. So let's see. What actually happened in the reaction? Well, these electrons stayed behind and we made a new bond. Okay, so that's what has to happen. So let's move the electrons to make this happen. So let's see, that means we have to have these electrons. These electrons have to come over here and make that new bond with hydrogen. The old bond with hydrogen, these electrons have to come and stay on that oxygen. So let's see, we had 2 lone pairs, we have 3 lone pairs now. We had 3 lone pairs, we have 2 lone pairs now. So that's right, we've done it right. The electrons that were supposed to move, moved, and everything's on the correct atom. All right, let's do the next one. Okay, so let's see. Okay, we have a negative charge again. So that negative charge is going to go over here. Oh, we're not going to attack that hydrogen because there's no hydrogen there. So what's it going to attack? It has to go for something partially positive, right? Oh, wait, hold it. This is a polar bond. It has to go for something that's electron deficient. So this is a polar bond. This side is partially positive and this side is partially negative. So I think it's going to attack there. Now, let's also look at the product side. Look, there's a new bond right here, and the bond is on the carbon. So we know those electrons are going to attack a carbon. And now we know why it's going to attack the carbon, because that carbon is partially positive. So let's go find our electrons that are going to do the attack. Okay, so the electrons that are doing the attack are going to be these electrons here. And so instead of attacking at this where we attacked the hydrogen, we're going to have them attack at this carbonyl carbon. And what that's going to do is that's going to move these electrons up to oxygen. So these are the arrows we have to make this reaction happen. These electrons are going to attack, these electrons are attacking the carbonyl carbon, and the double bond moves up onto the oxygen. All right, let's do the last one. Okay, wow, that looks like the product of the last reaction. But hell, let's do something about that. So let's see what's happening. We're going to reform the carbonyl, and we're going to have something leave with a negative charge. So how are we going to make that happen? First thing we need to do is pull these electrons in to give us our double bond. Then what has to break? Do we break this bond or this bond to make this product? Well, it's the one with the methyl on it. So that means we're not going to break the one with the OH. We're actually going to break these electrons on this bond and put them onto that oxygen. So let's see if that worked. We'll have a double bond. We'll have our OH still on there, and we'll have a negative oxygen with a methyl group on. So we followed the rules and we have the right product. All right, so that's the end of chapter 3. Thank you very much.